clean our wafers. Right? So that's the purpose to introduce this chapter 4. There are 3-tiered approach to control these unwanted impurities in silicon. Okay. The first one is a clean room, so we have to process this wafer in like special clean region, right? And so we can minimize the particles in this environment. Okay. We have a clean room in this campus, but not in this. The main campus is located in the 水源校区, okay, outside this, in the Gongguan region. We have a building, and there's like 2, 3, 4 floors. They are all clean rooms. Okay, so we have a lot of machines and equipment inside. And right now I'm the deputy director of that clean rooms. And tomorrow we will have a very special guest from your country. But yeah, I cannot say that. Yeah, I'm not allowed to, because they try to keep low profile. So some big people from your country, they will visit our. So I will show them around this clean room tomorrow. Yeah. If you are interested, you can ask me later. Okay. The second tier of this approach to control these impurities to clean the wafers, you can use some solution process to clean like the surface of your wafers. And the third tier of approach is to gather the unwanted material inside your wafers. Right. The first one is the environment, and then the surface, and right inside your wafers. So we will introduce these three ways, like how to get a clean wafers. And we have to do that because we have to control our yield, right? So that's very important steps to control your yield. Okay, so now we try to recap that what's the front end process in these features. Okay, that includes the cleaning. Okay, that includes the cleaning first here. Cleaning here, and also litho, oxidation, implant diffusion, deposition, and etching. Okay, those are the front end process. And here you can find out that for example, A is the material, starting material that we talked about in chapter 3. And okay, the B is the isolation, and C is the well. This is the well doping, and D here, there's the channel surface here. Okay, and E is the channel doping and channel strength. Okay, here. Then we have extension junction here. We have gate stack. This is the gate. And here we have some state or change capacitors. Okay, like here. And this is the elevated junction and contact. Okay, so we will introduce this in the following chapters. Okay. Okay, so again, I try to emphasize that we try to control the impurities and defects, because that will cause the yield loss. Okay, almost at 75% 95% yield loss is due to these particles. And we can do some optical inspection to monitor your starting wafer to check if it is a good quality one. So use this localized line scatters measurement to do this. And also these crystal originated particles called COP. This size, because you have some oxygen, and that will cause resulting some silicon dioxide in your materials, and this will affect your gate oxide integrity. So we can use some annealing hydrogen environment to decompose those oxide and reconstruct the surface and get this your oxide to make them precipitate from the deep depth in your silicon, which means we try to move away those defects. If we cannot eliminate them totally, at least we try to move them away from your channel. Right? That's the purpose. Okay. So this is the particles. Okay. It can be on top of these films or on the photoresist. And during this photoresist strip, you can also remove some particles, some these metals or alkali ions or some organics. Right? So that's the we can use some solution-based cleaning process to do this. Okay, and the importance of this defect is that will cause your transistor to vary their threshold voltage. And this is a threshold voltage equations, and we have some mobile charge density here, which are caused by these alkali ions. And for example, if we have oxide that's thickness is 10 millimeters, and if you have this QM like 10 to the 11 per centimeter square, and it will cost you 0.5 volt VTH shift. Okay, which is not good, because especially we have lower all operation voltage now, maybe less than 1.5 volt. So even 0.1 voltage VTH shift will change your characteristic of your circuits. Okay, so that's very important. And the second example to emphasize the importance of defects is the DRAM. That's this device. Okay, in this DRAM we have this is a capacitor that can store your charge here. Okay, you can use this B line and word line to read and write this capacitor's charge. Okay, but this charge, they are stored in this MOSFET, and they will be recombined if you have some defects in this device. Okay, that's defect, we call it Shankar-Lee-Hall recombination. Okay, and this Shankar-Lee-Hall recombination, we can use recombination rate to quantify this process. Okay, so here you can see that this recombination process depends on this sigma, which is the trap, this trap cross-section area, and you have VTH here. That's the minority carrier thermal velocity, and LT is the density of traps. Okay, so if this one change a lot, then that will affect your recombination rate, which means that the carrier you store in this MOSFET, they can vanish quickly, so you have to refresh this DRAM constantly. So that will cost more power consumption, right? So this refresh time is highly dependent on your defect density. So if we plug this number in this equation, this refresh time is like 100 microseconds. Okay, sometimes it's you have to, up to like several milliseconds. Okay, so either the transistor VTH will shift, or in your DRAM you have to refresh it in a shorter time. So then we have to control our defects or these impurities in our wafers. Okay, and also here's another example. This example show you during the oxidation process. From this figure, you can see if you increase the time, the oxide thickness will also increase. But there are three lines or three experimental data that show you the surface. How good is your surface, wafer surface? If you don't clean it, or you use sulfuric to clean, or you use ammonia to clean, then your surface conditions, they are quite different. So when you do the oxidation process, your surface, because the condition is different, so the growth rate is also different. Okay. Then once you have like very scaled device, then very small device, then this different surface treatment or the way you clean it will change a lot. Okay, so here are just some examples for you that, okay, if you don't control this, then you cannot get very good high yield in your process. Okay. Okay, now I think it's time for us to take a break.